Okay. So I want to do an example about linear transformations, or actually a couple examples. So the first one, example one, show, let me get some lines here. Lines. That might be too small. This would have probably best been done before recording. But what do I care? I don't have to watch this video. Yeah, you're just going to sit there. That's right. Okay. So, example. We'll do example one. Show that the transformation defined as taking the point xy and converting it into the point 3x plus y, 2y, x minus y, defines a linear transformation. And that transformation, you can tell the first point is in R2, and then we're converting it to some new point in R3. And then it says, find the image of the points 1, 2, and 2, negative 5. Okay. Sorry, these lines are too small. Let me do this. Let's go 125. Okay. Great, of course. All right. So there are a couple different ways you can think about the transformation. One of them would be to write this using vectors instead. Some students like to think of these as vectors instead of points. Doesn't matter to me what you choose, but if we did it in vector form, so vector form of the same equation, that would look like this. T of, and then xy equals, and then, whoop, don't need a that there. It'd be 3x plus y, 2y, x minus y. Okay. Doesn't matter which one you use. Well, let's actually do the images first. Those are simple. So the image of, here, I'll do 1, 2 in the point form. So 1, 2, well, you're just plugging in the x's and y's, so it's 3 times 1 plus 2, comma, 2 times 2, comma, 1 minus 2. Oh, don't need parentheses there. So the point 1, 2 turns into the point 5, 4, negative 1. Okay, and then the point 2, negative 5 turns into 3 times 2 minus 5, 2 times negative 5, and what is this? 2 minus negative 5. So what do we get there? 6 minus 5 is 1, negative 10, 7. Okay, so there are image points. You can tell they're definitely in R3, not R2, but they're defined from stuff in R2. Okay, now let's do the showing that it is actually a linear transformation. And so right here, I included the definition again of what a linear transformation is. We need to prove property 1 and property 2. Okay, so let's look at 1. So we need to show t of u plus v equals t of u plus t of v. Okay, and u and v have to be just any vectors in R2, right? So u and v have to be in R2. So we'll make them general vectors, because if you only do it with specific vectors, then you're not actually proving that it's always true. So let's let u equal, well, let's do these in column form, x1, y1, just so that you get used to seeing both forms. and v equals x2, y2. So now I've got two general vectors in R2, and I want to show that I want to take t of u plus v and eventually get t of u plus t of v. So t of u plus v is really t of x1, y1 plus x2, y2. And that's really the same thing as x1 plus x2, y1 plus y2 in one vector. And then I know that that turns into this thing right here. So it's 3 times the top part of the top component. So 3x, oh, I need this to be bigger because it's going to be 3-dimensional. So this is going to be 3 x1 plus x2, and then plus the bottom term. And then 2 times the y term, which is the bottom term. And then the top term minus the bottom term. x1 plus x2 minus y1 plus y2. Okay. And the goal is to get tu plus tv. So I need to kind of split up my 1s and 2s. So this is going to turn into 3x1 plus y1 plus 3x2 plus y2. And then I've got 2y1 plus 2y2. And then I've got x1 minus y1 plus x2 minus y2. And then that is the same thing as saying, this is a little overkill, but you guys, this is really the rigorous way of doing it, I suppose. 3x1 plus y1, 2y1, x1 minus y1 as one vector, plus 3x2 plus y2, 2y2, and x2 minus y2. And then that's going to equal the same thing as t of u plus t of v. So we prove in part 1. Okay, preserves addition. So now we need to prove that t of c times u equals c times t of u. I can just leave the c there, t of u, like that. So show this. We're not assuming it. So let's start with the left side here, t of c times u. Okay, so I know that that's the same thing as t of c times x1, y1, which is really, let's see, where's that definition again? Here, let me copy this. And we'll just paste it over here. Whoa, there we go. So this is going to be, actually, let's multiply the c in first. cx1, cy1. And now I can apply the xy rule over here on this side. So that's going to be 3 cx1 plus cy1. And then 2 cy1. And then cx1 minus cy1. And based on what we know about properties of vectors, we can factor out a c from each term, and that's the same thing as putting a c in front of the vector. 3x1 plus y1, 2y1, x1 minus y1, and then this is the same thing as c times t of u. So now we've proven that it preserves scalar multiplication. And then that's enough to say, because of 1 and 2, t from R2 to R3 is a linear transformation. Okay, so we've done example 1. And then let's do example 2 also here. So it's based on example 1. Remember, every linear transformation can be represented by just matrix multiplication of a vector. So we should be able to come up with a matrix that represents this linear transformation right here. So determine the matrix. We'll call it A, that defines the linear transformation this thing. Okay. Well, I mean, we can write this out a little bit. We know that T of xy should be some matrix A times xy, and that should give us this thing, 3x plus y, 2y, x minus y. So if we do a little bit of analysis, this matrix right here is 3 columns, or 3 rows and 1 column. This matrix right here is 2 rows and 1 column. And this matrix right here then, in order to get a 3 by 1 as the product, this is going to have to be a 3 by 2 matrix. Right? Because remember, these guys have to be the same, and then the resulting matrix is those guys. So we need a 3 by 1 matrix. So let's write it like this. I'll call this A, U equals B. So A is a 3 by 2. So A11, A12, A21. You'll see pretty soon this is somewhat overkill here. Whoops, that needs to be a 1. A31, A32. And then right here I'm going to put xy. And then I know that my result has to be 3x plus y, 2y, x minus y. And what you could do is you can multiply out this side and end up with some system of equations when you set them equal to the things in the b vector here. But you can actually do this one pretty quickly in this example because there's no, like, I don't know, it's just simple. So if you think about it, the first thing that you're going to multiply, a11 times x plus a12 times y. So I'll do the first one right here. a11 times x plus a12 times y. That's got to equal 3x plus y. Well, that means a11 has to be 3 and a12 has to be 1. So we can actually get a pretty quickly here. A has to be 3 here and 1 here. And then to get the 2y in this row, I'm going to be multiplying these guys by this. So I want no x terms, so 0 here. And I want 2 y terms, so 2 here. And then to get this, I want 1 x term and negative 1 y term. So 1x, right, when I multiply this by x, and then this would have to be negative 1 times y. So here is the matrix representing the transformation T. And since it's 3 by 2, you can tell that it takes a 2-dimensional vector and turns it into some sort of 3-dimensional vector. Okay, hope that helps some.